Welcome to Opening Voices. I'm Quentin, CEO of Clever Cloud. Today we are meeting with Philippe Notton, the CEO of SiPearl, the European company specialized in processor design. In this episode, we introduce SiPearl and explain what is a processor. Hello, and welcome to Open Voices. I'm Quentin and I am traveling around Europe to find a good tech leader and explain what we are doing in Europe to create the new technology and the future. Today we are in Paris, precisely in Maison Lafitte, with Philippe Notton, to discuss about SiPearl, semiconductor and stuff. Hi, thank you very much for welcoming me, Philippe.
Bonjour Quentin. Thanks for this opportunity to discuss semiconductor, SiPearl, compute chips.
So, first and foremost, when is the year when we created SiPearl?
The company has been set up in June 2019, and the first employee started in January 2020. So we're a bit more than 5 years now.
So it's a company which is 5 years old, and the purpose of SiPearl is what?
So we are a pure semiconductor fabless company. The motto is to build compute chip, starting with high-performance CPUs.
Okay, so there is a lot of things to discuss that. The first thing is it's a fabless company. Maybe here we can explain a little bit. So first, what is a semiconductor? Is the chips that power IT? What is the difference between a small chip like can produce ST microelectronics and what does SiPearl? Maybe explain a little bit.
So that's the full challenge of understanding what is semiconductor. So it starts with a diode, which is you have 10 diodes per sense, to an NVIDIA H100 on the other side of the spectrum, which is $40,000. And in between, you will have some microcontroller, $1, for instance, that's what ST is doing. You will have some image sensors, a couple dollars. You will have some baseband processors like the one you have in your phone, or something like $100. You will have some semiconductor focused on radio frequencies for transmission, which can be a couple dollars, so it's quite wide. On our side, so what SiPearl is doing, it's at almost at one of the extreme of the spectrum, because we are talking about CPUs, which are, let's say, their value is, let's say, a couple $1,000s per unit in terms of price, but also with a computing power that you will not find in a microcontroller.
CPU stands for Central Processing Unit. It's a kind of the computational unit which is in the heart of every computer.
In all cases, everywhere you have a CPU. CPU is at the opposite of accelerator or GPU. A CPU is generic, can do everything. But if you want to have something very focused, for instance, cryptographic operations or graphical operations or quantum operation, in this case, you need a dedicated accelerator.
What I try to explain at the beginning of the people about semiconductor is there is mainly three kinds of semiconductors for me. One is ASIC, which is a semiconductor which has the implementation of the algorithm inside it. So if you want to change it, you basically need to regrave it. You have FPGA, which kind of programmable ASIC, but maybe you can temper a little bit there. And the one which are more versatile, which are not the most efficient, because ASIC is very efficient, but are the most versatile, and that's the one we build computer with. And the two others are some things we will use as a peripheral and coprocessor. Am I right when I explain that?
I may add another category, which is so-called ASSP, application standard product. So, and especially in the past, where the cost of designing a chip was reasonable, let's say for 1 million, a couple million, lots of, let's say, industrial company who are used to develop or have developed their own ASIC to fulfill a very specific demand. So I have a specific operation I want to do. I can give, let's say, 1 million to a service company, and this service company will build a specific chip just for me, which will be fully suited for my needs.
And it's still something that happens, or
yes, it still happens, but it's just more and more expensive. Because, for instance, if you want to have a very specific chip for a compute need or something like this. For instance, Apple, they have developed their M2 processor, M3 processor, and we may back to this later on.
So it's become more and more expensive. It's still ongoing. Maybe we can explain a little bit there of what kind of semiconductor. So if, for example, you have a router, which is the kind of device would manage a network inside your home with your live box, have a small router. But on data center, you will have big router on top of the rack and a small switch on top of many racks and aggregate. You will have a CPU, small one, and a big ASIC to manage the router, and the ASIC will be managed by the CPU, but the ASIC will do all the complicated and very quick stuff.
It's a good example. So you will host the operating system or the specific network operating system on a CPU, which can be a generic one. But imagine that, for instance, Cisco is building this router. It's going to be a router or switch with 48 ports. I need to manage these 48 ports. I need to develop a very specific chip that will have these 48 IOs, a huge throughput connected to my CPU. But as Cisco, I have the budget, I have the volume, and I have the budget to have designed a very specific chip to manage all this routing. But if I'm a startup, or if I want to build my own router with, let's say, a couple units to produce, it will be completely insane to develop a chip on demand because I will never have the money back.
Maybe what we can explain there is what we call the cycle inside every semiconductor system, and explain what will be the difference between the three. And after we will focus more on the CPU. What is a cycle? What we call a processor cycle or a semiconductor cycle?
You mean at instruction level?
Yes.
So even, let's say, if we go back in time 40 or 50 years ago, where you had some more, let's say, early CPUs, or 60809 or 6502 or Z80, that you may remember, the datasheet was only a couple pages. You had something like 50 or 80 very basic instructions. So for instance, in one clock cycle, at this time, it was something like 1 microsecond, so 1 million operations a second. It was possible to do very basic computation, addition of 2 8-bits number, so below 255. And in one clock cycle, you had the possibility to do this basic instruction. Now, what has changed is that the instructions are much, much more complex. So in one clock cycle, you can, in some cases, multiply 2 vectors. You can, in some cases, multiply a matrix. And what has changed also is that it's no longer 1 million instructions per second. It can be 3 or 4 billion instructions per second. So the instructions themselves are much more complex, much more powerful, and you do much more per second.
So if you know you will do a lot of the same algorithm, you engrave it inside an ASIC. In one instruction, you will have everything performed. So it's very powerful. But you need to have it like doing all the time, because it's the only way it will cover the cost of this, and you will be Cisco and stuff. And on the other side, there is a kind of instruction you cannot really do inside the CPU, because you don't have the space to engrave everything, and you will have a coprocessor there, and enter, for example, the graphical card for NVIDIA. That's it?
That's correct, yes. And because if you want to do a specific computation, for instance, a matrix computation, it's either you do it by CPU. So in this case, you have all the partition of the matrix computation. You need to do some sum, multiplication, etc. It's going to cost you multiple cycles to do it. Or if you want to do it in one cycle, you need to develop or write a specific hardware to do the matrix computation. So hardware means extra square millimeters in terms of silicon production. So it means extra cost. And if you want to afford this extra cost in your chip, in this case, you must use it. If not, you just carry some spare square millimeters on the chip. You pay it for nothing. So if you develop it, you need to use it.
So basically, the matrix of silicon is the square millimeter cycle, the way you engrave stuff on this, and a good product is a product which use easily every part of the square millimeter, because in a perfect world we can figure out a very big stuff with every operation engraved inside, and it will be simple. But what you say, it will be so expensive that it will never be affordable and will be sustainable for a company to buy it, isn't it?
That's absolutely correct. at the end, it's a product. You need to produce this product, so you have a cost per square millimeter, small chip, big chip. Ideally, everything has to be used. If not, you just carry some dead bodies on the chip and some square meters you will not use. And the more powerful is the chip, and that's what happens now. They are, let's say, larger and larger with more instructions, more computing capacity, and of course, much more power, which is used to manage them.
Okay, so that's the point of view of what is a chip. So SiPearl is more focused on the CPU. So CPU, the CPU landscape is what today? Who is producing CPU, and what is the CPU landscape? And after we will focus on what exactly does SiPearl.
So here we are talking about CPU, advanced CPU. So the one that you will find at least in a server or supercomputer. We are not talking about microcontroller that you will find in your dish machine, which is another.
Yeah. Okay, we will speak about a CPU. We'll go to a computer,
Okay.
Laptop, and server. Okay, maybe it can be interesting. We cover the laptop, and maybe even the very small laptop with no keyboard you can have in your hand, which is at the end a smartphone.
So let's say the historic player on CPUs has been Intel, complex 86 instructions. Then AMD did the catch up and are well deployed. That's for the, let's say, x86 ecosystem. And for
when we say x86, what we describe as the x86,
that's the, let's say, so-called instruction set, and that's the way through the software and the application you have access, or you use some assembly language. You partition your code into very basic instructions like multiplication, addition, shift, vector computation. x86, that let's say the historic instruction set. Other instruction set happen, MIPS, the new computer business, which is now on the way down. RISC-V, which is one of the important trends, let's say, for the next decade. ARM.
We will speak a little bit about RISC-V.
ARM, which is, let's say, mainly coming from the mobile phone industry, which is now quite powerful, and that's what you're using in data center and in HPC. So that's, let's say, different class of software and instruction set.
And basically, if I have a software who runs on x86, can I take it and put it on ARM?
No. Okay. No, you need to recompile it. The application can be the same, or the user experience will be the same. You need to recompile it because it's targeted to a specific processor. Now, an ARM processor can be compliant with another ARM processor. Same with x86. That's why the code which was working in your laptop 30 years ago, today is still working because it's still x86 instruction set. And Windows did all the tricks to ensure it's compliant. That's a legacy.
Okay. So basically, the whole landscape was so because like 40 years ago, there was producer in Europe of CPU. There was many people trying to create some CPU and stuff, and at the end, it contract to basically Intel and AMD.
And newcomers. No,
the newcomers
in terms of CPUs.
Let's talk about the market 5 years ago, and we speak in the next episode about the newcomers. So it retracts to that, and everything around the x86.
That's, let's say, up to 10 years ago, it was the case, yes. And it has been contracted, and especially in Europe, due to the cost of development. Because to build complex products, you need lots of money, and to have lots of money, you need investors, etc. And that's maybe something we avoid lately.
And 10 years ago, we start discussing in Europe about the problem that AMD and Intel are American. And we maybe we need some CPU designed, and we will speak about the production a little bit later, in Europe. So that was a huge introduction about what is an instruction set. And I hope it will not lose you. So ask any question on the social media if you have some question about that. And next week we'll continue about the revolution coming to the CPU with the ARM and RISC-V.
See you next week.
Thank you for listening Opening Voices. We will continue our interview with the SiPearl team in a few days. So follow us and subscribe not to miss our next episode.